Howdy, today on Film Science we're looking at the reactions of metals. So the science understandings that we're going to look at are the reactivity of a metal affects its ability to react with other chemicals. So investigate reactions of metals with water and acidic solutions. Compare the vigor of reactions of different metals with their position on the metal activity series. And write equations and half equations for reactions between metals in a given acid. When I go traveling, I like to look at big metal structures because oftentimes some of the most impressive structures are big structures made out of metal. It's fun to have a look at where they're reacting and how they're reacting. So here's the Sydney Harbour Bridge, and here is a nice big spot of oxidation here. So there's rust forming. This is the Golden Gate Bridge in San Francisco, and again you can see where the paint is flicking away from the orange bar here. This is just above one of the supporting legs. The legs was built in this concrete area here where they sucked out the water from. This is the Eiffel Tower in Paris, and again we can see where the paint is flicked away. We can see some oxidation of the metal underneath it. Now, all three of these structures are made of iron. In these two cases it's steel. In this case it's iron, wrought iron, pig iron, which is a bit more brittle than the steel that was used for the Sydney Harbour Bridge and the Golden Gate Bridge. Down here, this is the back of the Statue of Liberty. It doesn't really look like it. It is. It's an angle you don't normally see. Again, the copper has oxidized. It was brown when it was first built, but exposure to the oxygen in the air and sea air with salt and water, you get an oxidation happening, so you get the verdigris, the pretty green colour of the copper. All of these are down to the reactivity of the metals and them reacting with their environment. So let's have a look at some of the reactions of metals. So let's have a look at some of the reactions of metals with water, for example. So down here I have a lump of sodium that's going into a solution of water and phenolphthalein, which is an indicator. And thanks to Reese Lewis for the videos, and in fact all the videos in this video. As it's reacting, you get a hydroxide ion being produced from the metal, and when it's reacting with the water, and also some hydrogen gas, and that's what the bubbles are that are forming. Now, hydrogen gas is quite volatile, so if there's enough heat energy it should catch on fire, and as it catches on fire we can get explosions happening sometimes. So that's an example of a metal reacting with water. So you probably wouldn't make a bridge out of sodium for many reasons, but one reason is the sea air wouldn't be very good for it. It would explode pretty much straight away. So let's have a look at the reactions here. So sodium metal is reacting with water. Now we're making a hydroxide, so that's going to be sodium hydroxide, and we're also making hydrogen gas. So now we need to make this balance. We've got too many hydrogens over here. We've got 2 hydrogens, 3 hydrogens, but only 2 on this side. So we need to make 4 hydrogens in total. So if we double that, now we've got 2 hydrogens, but now we need 2 sodiums as well. And we're going to need 2 waters. So we've got 4 hydrogens, 1, 2, 3, 4 hydrogens, 2 sodiums, 2 sodiums, 2 oxygens, 2 oxygens. So now we're balanced. So in this reaction, we're acting a very reactive metal, sodium, with water, and we get a hydroxide being produced and hydrogen gas. Now, sodium is a very reactive metal, so it will do this, but less reactive metals won't. So if you put gold in water, you won't see gold hydroxide forming, and you won't see any bubbles of hydrogen, because gold is very unreactive. So the reactivity of the metal determines whether this will happen or not, and also how fast it will happen. So let's compare some different metals. So here we have lithium, here we have sodium, and here we have potassium being put in water. So if we have a look, we can see that potassium is reacting really, really readily. We can see the lilac flame of potassium being generated, and it exploded pretty quickly. The lithium, each little chunk of lithium is reacting relatively quickly, but if we had a similar sized chunk of the lithium and the sodium, we would see the sodium is reacting a lot faster. You see the sodium forms a little ball and then it moves around on the surface. The lithium chunks, they are still there and they're reacting relatively slowly. Part of the problem with this is the hydrogen generated makes a bit of a casing around the metal, so it doesn't contact the water as much, so it reduces the reduces the rate of reaction. But if we have a look, we can place these metals on an activity series. So we've got potassium, which was much more reactive over here than the sodium was. So the potassium is more reactive than the sodium, and then the lithium would be further down again. Now, sometimes you'll see lithium at the top of an activity series, and there's a very interesting reason for that. Now, we're not going to go into it, but lithium does lose its electron relatively easily particularly when we're looking at things like batteries, and that's why lithium is often found in batteries. But at the moment we're just looking at the reaction with water. So we can generate these metal reactivity series, and we can see that as the metals become less and less reactive, what they react with changes. So potassium, sodium, lithium, they were reacting with water quite readily at room temperature there. With calcium will do this as well. But something like magnesium, if you put it in water, it will react with water. It's just very, very, very slow, and you won't see the large amounts of bubbles being produced, and it will take a very long time for the magnesium to dissolve in the water. But all of these metals will react with acids. Acids are quite reactive, so all of these metals here will react with acids. But again, as you go further and further down the activity series, the reaction is less vigorous. So we're going to have a look at magnesium in acid shortly. Reacting with oxygen, so oxidizing in oxygen. So again, all of these things will react. Potassium, when you take it out it's kept in oil because it's so reactive. As soon as you cut it, it starts reacting with oxygen in the air and producing an oxide layer. So it's very, very quick. Whereas something like silver oxide layers form over, it can be years, decades. This is why silver needs to be polished over time. But its reaction with oxygen is very, very slow. And then you have something like gold and platinum. They're both very unreactive metals. They don't react with much. So that's an activity series. So let's have a look at magnesium in acids. So this acid is hydrochloric acid. This one is of a higher concentration than the one on this side. We see as it's reacting, it's producing bubbles, and those bubbles are hydrogen gas. And we're also getting a salt being produced, but that dissolves into solution, so we can't see it. So this one has finished because the acid is of a higher concentration. This one is taking a bit longer for it to go. So let's write the reaction. So a metal in an acid produces a salt and hydrogen gas. So we have magnesium. Our acid is hydrochloric acid. Okay, so we need to make hydrogen gas over here, and our salt is going to be the metal ion and the negative ion from the acid. So in this case it's a chloride ion. So it's going to be MgCl. Now, magnesium forms a 2+ ion, chlorine forms a -1 ion, so we need 2 of the chloride ions to balance out the charge of the magnesium ion. And we've also got 2 hydrogens over here, so to balance it, 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines, and 1 magnesium, 1 magnesium. So magnesium is fairly reactive, so it will react with acid to produce a salt and hydrogen. But less reactive metals won't react, or they'll react slower, and indeed things like gold won't react at all. Gold can be dissolved in aqua regia, which is a combination of acids, but it's very, very dangerous. So now we need to compare vigor of reaction and activity. So here I have some zinc granules, and to that we're adding some hydrochloric acid again. So if we want to compare vigor, we need to keep our other variables constant. The only thing we're going to change is the metal. So if we have the same quantity and concentration of acid, the same quantity and surface area of both zinc and magnesium, so these are the metals we're comparing, which one would react more vigorously? So then you need to look at your activity series to figure out the answer. So here's magnesium, so put a little dab there, and then here we've got zinc over here. So we're comparing magnesium and zinc. Magnesium is more active, so therefore we would see a much more vigorous reaction from the magnesium than we would from the zinc. Now, in the case of the videos we've just seen, we can see it's a very vigorous reaction. We're getting a lot of hydrogen gas being produced. But the vigor does depend on the activity, as well as some of the other things, like we've got here, quantity and surface area too, that can change the vigor. So that's right, the reaction of zinc with the acid as half equations. So the zinc starts off as solid zinc, and that goes to zinc ions. We do make a salt, so the positive part of the salt is the zinc ions. Now zinc makes 2+ ions, and to balance that out we need 2 electrons. Okay, so we've got zinc making zinc ions and 2 electrons. Then we've got the hydrochloric acid, that goes to hydrogen gas, so from the hydrogen, and we get some chloride ions as well. So we're going to need 2 of these and 2 of these. And now if we look at our charge, we can see that we've got a charge of 2- on this side, so 2 chloride ions, but there's no balance over here for that negative charge. So we need to add our 2 electrons to this side to balance out what's happening here. So now we can write our overall equation. So zinc plus, now we've got 2 hydrochloric acids here, 2 HCl, 2 electrons and 2 electrons on either side of the arrow, they'll cancel out. So then we go to zinc ions plus 2 chloride ions plus hydrogen gas. So now we've written that out. Now we could write that the zinc ions and the chloride ions as zinc chloride, which is the salt, plus H2. And we can put our states in as well. So we had solid zinc, hydrochloric acid is dissolved in water, so that's aqueous. If we go down here, the zinc chloride dissolves in water as well, so that should be aqueous, and hydrogen gas is a gas. So we can write the reaction of the acid with the metal as half equations and then add it together like we would any other redox reaction. So how does this relate to the real world? So unreactive metals, so metals that are further down in our activity series, you can often find them in the ground as themselves. So gold nuggets, for example, are pretty much pure gold. You can find silver in the ground as silver. You would never find a lump of potassium or sodium or lithium in the ground because they're reactive. They've already reacted with something else in the environment. So you never find them as their native metal. They are very easily oxidized. They'll react with oxygen in the environment. They'll react with chlorine or carbon or many other substances, silicon. They'll react with those in the environment to produce a substance that is the metal ion locked up. To form the metal, you need to reduce the metal ion somehow, and that's how more active metals are made. And we'll have a look at that in electrochemistry. So this relates to the discovery of metals too. Metals like copper, mercury, silver, even iron, tin and lead, they've been known about for a very long time because of their lack of reactivity. They're relatively easy to find in the environment, and also for something like iron, reducing its ions is relatively easy to do. It doesn't require much energy to do that. So because of that, we've known about these for a long time, but these more active metals we haven't known about for as long. So something like aluminium, I'm going to talk about in a second, it's only been produced in large quantities for 150 years or so. And substances like potassium and sodium, we didn't have solid lumps of those until people figured out the chemistry to produce really active metals. So let's have a talk about aluminium. So let's have a quick talk about aluminium. This is the Washington Monument in Washington, D.C. When I went and visited, there'd been an earthquake not long before, so they'd put a lot of scaffolding up, and they'd also fenced it off so you couldn't get close to it because they were repairing it. It was the tallest obelisk in the world. And right on top there is a pyramid of aluminium, which seems like a very odd thing to have on top of a monument like this. You might have something like gold, which is very precious. But at the time that this was built, aluminium was ridiculously precious because the production process for producing aluminium from its mineral, bauxite, so this is bauxite down here, it had only just been invented, so solid aluminium was very rare. So this little pyramid was worth a lot more than gold would have been to put on top of the monument. If we go back here and we have a look at our activity, we can see that aluminium is quite reactive. So why would you put it on top of a monument if it's very reactive? The thing with aluminium is it's so reactive that it produces a coating of aluminium oxide that protects the metal underneath. So you get this coating of aluminium oxide where it's reactive with oxygen in the environment, and that protects all the aluminium underneath. And this is why we use aluminium in things like cans for soft drink or food. So the aluminium, it's quite light, which is an advantage, so it's easy to transport, but also because it produces an oxide layer, it protects itself. So today on Flipping Science, we looked at the reactions of metals and the activity series and how that relates. That's it for Flipping Science today. See ya.